Good morning. We've been working on calculating the electric charge distributions on macroscopic objects. So charge uniformly spread out on the surface of some macroscopic object. And last time we worked on a uniformly charged, really thin rod. And we found that we were at a very special location, which was along the line bisecting the rod, perpendicular to the rod. We were able to get an analytical expression for the electric field, although we couldn't get it at other locations. But for locations kind of near the midline of the rod, it looked like that was a reasonable approximation. And we also looked at situations, special cases. We looked at a case, we got an approximate result if our observation location was quite close to the rod compared to the length of the rod. And we find that in that case, we got a nice simple algebraic expression. The field fell off as 1 over r. So these approximate expressions are our friend. What you should have gotten out of this discussion is not to memorize the electric field of a long uniformly charged rod, but this approach, this procedure for finding the electric field of charge distributed on some macroscopic object is a very general approach. It works anywhere, although you can't necessarily use calculus to get an algebraic expression. We may have to do it numerically with a computer, but this is always what we do to add up the contribution. So we divide the object into small pieces whose field we know, and we'll see that that's usually a point charge, but it doesn't have to be. And then we spend a fair amount of time. The piece that took time was getting an algebraic expression for delta E, because it involved a lot of stuff that's implicit. You had to pick an origin. You had to pick axes. You had to get locations of your piece and locations of your observation location in this coordinate system. You had to calculate the vector r. You had to find out how much charge was on that piece. So there's just a lot of geometric and physics setup that goes in there. That's what this is really where most of the work is. But if you don't do step 1, you're a little bit lost, as some of you discovered in recitation, that if you don't actually pick a representative piece and try to draw these quantities on a diagram, then it's kind of impossible to pick an origin and axes and find distances and things like that. This is just math. Somebody does it. You do it yourself. Your calculator does it. Wolfram Alpha does it. Somebody does it. Your computer does it. And then checking is extremely important. We checked units to make sure we really got newtons per coulomb, because if we didn't, we probably hadn't really calculated electric field correctly. And we looked at special cases. So if you got really, really far away, did it look like a point charge? And if you're really close, is there some simplification that makes the field kind of interesting? So that's what we're doing, and we're going to continue that today. Okay, suppose you were calculating the electric field of a cube that had been uniformly, a plastic cube, been rubbed with wool or something, a glass cube that had been rubbed by silk. And so the side of the cube is length L. You're at some location X from the center of the cube. And you find an expression for the electric field of the cube that is Q over epsilon 0 L over the square root of x. Is that a plausible expression for electric field? You like that?
You wrote it up there, so I'm going to say yes.
Ah, but you calculated it.
I did.
So how do we decide if this is plausible or not?
Well, you know that if the L is going to increase, then it's probably going to have a larger charge, and that makes sense. And also, the square root of the distance, usually it becomes kind of distance, so that's going to...
So it has a distance dependence, and the charge, the field should increase if the cube gets bigger, and that makes sense. What's another way we can check this answer? Ah, units. So let's check the units, okay? What do the units come out to here? If the units of 1 over 4 pi epsilon 0 are Newton meters squared per Coulomb squared, what are the units of 1 over epsilon 0? They're the same, right? 4 pi doesn't have any units, right? So here we've got coulombs on top, Newton meters squared per Coulomb squared on the bottom. We've got meters. We got meters to the 1/2. Oh, sorry, Newton meters squared per Coulomb squared should be in the... So what do the units come out to? Do they come out to newtons per Coulomb? No. We've got a problem. Okay, so it's a real quick and very powerful check, because it tells you that this can't be a legitimate algebraic expression for the electric field of anything, let alone a cube. Okay, so you try this again. And this time you get an electric field that's 1 over 4 pi epsilon 0 50 QL over x cubed. So what about the units? Newton meters squared per Coulomb squared. Coulombs, meters, meters cubed. So it does come out to newtons per Coulomb, right? So the units are okay. What other check could we apply? If we get really, 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 then it should look like a point charge, right? So it should be 1 over x squared when you get really far away. Is it? It's not, is it? It still looks like 1, because L is a constant, so it looks like 1 over x cubed, which suggests that this is still not a reasonable expression for the electric field of a cube. So there's some really easy checks you can do that are powerful and important. So this step 4 is not just something your instructor told you to do. Step 4 is actually a part of the physics. Okay. So comments about that? Questions? No. Okay. So the next thing we want to try to calculate is the electric field of a uniformly charged thin ring. And so here's a ring on the in the YZ plane, and so the axis of the ring here is actually, let's put the ring in the XY plane so that the axis coming out is Z, because that's more like cylindrical coordinates, which makes some sense. So we'll call the axis the Z axis. Where do you think we have a shot of getting an analytical expression for the electric field of a charged ring? At center, okay. Where else? Along the surface, well, it's going to be pointing out in some interesting ways. So that's going to, I mean, we can do that. Analytically, it's going to be tough, but along the axis seems like a possible place, right? So what we're going to do, and that actually turns out to be more useful than you might think. So what we're going to do is follow this procedure to calculate the electric field of a uniformly charged ring at some location along the axis of the ring. It's not that everything's made of rings, but it's going to turn out to be useful in some things we want to do in a minute. So we'll do this. So the first thing we have to do is, step one, divide this ring into pieces and draw R from our representative piece. So representative pieces probably should not be on the X or Y axis. So some piece in the middle to our observation location somewhere on the Z axis, and then draw the electric field that we should get from that piece. So here is here's our piece, and you can see why I'm doing this in VPython instead of trying to draw it on the board initially to show you where we really are. So we have a little piece here, and our observation location's on the Z-axis. So the green arrow is R, and then that little purple arrow is the contribution delta E of that little piece of the ring. So now what we need to do is work on the algebraic expression part, and I'll do the best job I can of drawing in 2.5D here. So here's our observation location. Here's our little piece of the ring. Here is R. It seems plausible that we would put our origin at the center of the ring. So we'll put the origin at the center of the ring. So this is X, Y, this is Z. So our observation location is simple. It's just Z. And the location of our little piece is going to be easier to do with angles, right? Because what we want to do is march around the ring. So we'll draw the radius. We've got some angle theta. And so the location of this piece, and then our little piece has some angular width delta theta. Or if you want, an arc length of RD theta. Okay? So the location of our piece is now r cosine theta, r sine theta 0, which means that the vector r is going to be 0, 0, z minus r cosine theta, r sine theta 0, or minus r cosine theta minus r sine theta z. Because of the symmetry of spheres and cylinders and all that, we probably need to get used to working in cylindrical or polar coordinates here. Okay, now, interestingly, so our little delta E here has x, y, and z components. So we're going to approximate the ring as point charges. We're going to take this little piece and say it's a point charge. So now how much charge, if the ring has charge Q, how do we figure out the charge on one piece? We'll call that delta Q. Now this is important because usually our integration variable or summation variable kind of emerges from this, so we have to be careful with it. Yeah, Carlos.
Can you just be the circumference divided by the number of pieces that we divide a ring into?
Okay, so the circumference by the number of pieces we're dividing it into gives us the arc length of one piece, right? But that doesn't give us a charge. Okay, so you're saying 2 pi r over n. So what are we going to do with that exactly?
Q divided by n.
Well, it's q divided by n, right? I mean, it's q divided by the number of pieces for sure.
Assuming it's uniformly charged around.
Well, it is uniformly charged, yes, we're assuming. It gets more interesting if it's not. Well, there are two standard ways to think about it. One is the charge per unit length times the length of this piece. So we could say this is going to be equal to Q times the arc length of our little piece divided by the circumference, right? Okay, so that gives us, this is a unitless fraction, and the arc length is of our little piece in our terms is what? What's the arc length of this little piece here? If its angular length is delta theta. Yeah, r delta theta. So this is just equal to r delta theta over 2 pi r, which gives us the r's cancel, and we get q times delta theta over 2 pi. So this is the angular length of the piece, and this is the number of radians in a circle, right? Okay. So now, and so did we get a summation variable, an integration variable emerging from writing delta Q? Yeah, we got that delta theta right, and that's good because we certainly are going to want to sum around theta here. Okay, so we have a 1 over 4 pi epsilon 0. We have a Q, which is a charge of the whole ring times delta theta over 2 pi. We have a 1 over r squared. Well, what's the magnitude of r here? So the magnitude of r is going to be the square root of minus r cosine theta squared plus minus r sine theta squared plus z squared. But what is this? Yeah, that's an r squared, isn't it? So we just get a square root of r squared plus z squared. So this is r squared plus z squared times r hat, which is minus r cosine theta minus r sine theta z, divided by r squared plus z squared to the 1/2. Right? Yeah.
Where did you get just the r squared from in the magnitude?
Because sine squared theta plus cosine squared theta equals 1. So r squared times sine squared theta plus cosine squared theta is r.
Yeah.
Thank you. Okay, now, so we have to divide this into x, y, and z components and write them out. But what do you think is going to happen here? When we march around this whole ring, adding up little pieces of delta E, what's it going to look like? Well, let's see what happens when we do it with a program here. So we have here, let's look at it head on. So as we march around, we have little contributions of, we're drawing delta E for each of these little pieces. So that's all the little delta E's that we have to add up to get E net here. What's going to happen to the x and y components? They're going to cancel, aren't they? So we're just going to get a kind of a large field in the z direction. So all we really have to worry about is the z component, right? So we have delta E sub z is 1 over 4 pi epsilon 0 q delta theta over 2 pi times z over r squared plus z squared to the 3/2. And so we could turn this into an integral, presumably. We just let delta theta get really small and turn into a d theta. And so we would have Ez is the integral of 1 over 4 pi epsilon 0 qz over 2 pi r squared plus z squared to the 3/2 d theta. And what are our integration limits? 0 to 2 pi. Now, what's the only thing that depends on theta in this whole expression? This is a super easy integral because q is a constant, z doesn't depend on theta, r doesn't depend on theta. It's basically an integral of d theta from 0 to 2 pi, right? Which is pi. So we've got a 1 over 4 pi epsilon 0 qz r squared plus z squared to the 3 halves times 2 pi. So the pi's cancel. We get a 2. And so we now have an exact expression for the field on this axis of E sub z is 1 over 2 epsilon 0 qz r squared to the 3 halves. Yes?
Shouldn't it still be 4 pi epsilon? Because in the integral you have qz over 2 pi. So then the 2 pi should cancel out.
Not the 2 pi.
Right, you're right. You're right. Yep. Thank you. You're quite right. Better. Thank you. What about units? Well, what do we get? We got Newton meters squared per coulomb squared. Coulombs times meters divided by meters squared to the 3 halves, which is meters cubed. So we got meters cubed on top, we got meters cubed on the bottom, we got newtons per coulomb. That looks plausible. Okay, what happens? So what about this? Does it look like a point charge when we get really far away? So what does it mean in terms of these algebraic quantities to get far away from the ring? What is bigger than what?
Z is much bigger than
Z is much bigger than R, isn't it? So far away, if Z is much bigger than R, 1 over 4 pi epsilon 0 QZ over, okay, we have an R squared plus Z squared to the 3 halves. If Z is much bigger than R in this sum, we can neglect R. So we get a QZ over Z squared to the 3 halves, which is a Q over QZ over Z cubed. Q over Z squared looks like 1 over Z squared, falls off like a, with distance like a point charge. So there's one other special case we can check. What should the electric field be if our observation location is actually at the center of the ring? It should be 0. It should. So let's see if that works out. If Z equals 0, that's a 0, so it comes out to 0. So makes sense. Can you sketch a graph of the magnitude of E as a function of Z? What would that look like? For point charge, it's easy, right? We just have this 1 over r squared. If you go right to the point charge, it goes to infinity, right? Okay, so what did you just tell me it had to be at the center of the ring? 0. So it better be 0. And what do we decide it had to be doing over here? Falling off like 1 over r squared, right? So it's got to be looking something like that. What's got to happen in between? Got to go up and come down, doesn't it? It's got to do something like that. So there's actually going to be a maximum at some distance, which is kind of an interesting distance dependence for this field. All right, questions about that? Okay, now that we've done that, we can actually use it to calculate the electric field of something else. So suppose we have a disk, a circular plate that's been uniformly charged. And we want to find the electric field somewhere, again, on the axis here. But we could divide the plate into point charges. But what else could we do? Yeah. We could use rings. We could use rings. We know the electric field of a ring. So our piece, whose field we know, could be a ring. So we'll draw some representative ring here. It's got some thickness. So here's our ring. So we basically can think of this disk as a lot of concentric rings, all contributing to the electric field, which is still going to be along the axis. Okay, so what is our integration variable going to be in this case?
Delta R, the radius.
Yeah, it's going to be r, isn't it? So the location of the ring is given by some little r. And its thickness, it probably better be a delta r, where the radius of the disk is capital R. And so we know the field of a ring, which I just erased. So EZ ring is 1 over 4 pi epsilon 0. What was it? QZ over r squared plus z squared to the 3/2. Is that right? Yeah. So for this case, since r is our variable, this is going to be the little radius, and this is going to be a delta q. So this is our delta E sub z for this ring. So now the question is, again, delta q, the amount of charge on this ring. Do all the rings have the same charge? No, they don't, right? The bigger the ring gets, the more charge it has on it. So delta Q is going to be something like the total charge of the ring divided by, in this case, the surface area of the ring. So that's going to be pi capital R squared. I mean, sorry, the surface area of the disk. So this is for the disk. And now what's the area of the ring? So imagine taking this ring and slicing it and stretching it out. It looks like a rectangle, basically. So its length is
the pi delta R squared minus pi R squared?
not that complicated. So it's the length is, so if we stretch this out so it looks like a rectangle, its length is 2 pi r, and its width is our delta r, right? So here's our integration variable coming out. So we have the area of the ring. In this case, it's q over pi r squared times 2 pi little r delta r. Yes?
Could you also do just like a big circle, like subtracting the inner circle out of the ring, like this area?
Oh, get the, oh, so you want to get the area of the surface area of a disk this size and subtract the surface area of a disk this
That's what
size?
I had thought.
Oh, I see. Okay, well, it should come out to the same thing. But this has the virtue that, well, you'd get a delta r out of this one too. So you'd have to make that at r and an r plus delta r, and yeah. But yes, in principle. And so dEz is just going to be equal to 1 over 4 pi epsilon 0 q. I'm going to write it as q over a because it's the the charge per unit area, per meter squared of the disk. Because it turns out, if the disk is big enough, it doesn't really matter if it's circular or square or rectangular or whatever, as long as we're close to it. We can't even see the edges. Times 2 pi r dr. So that's our delta q times z over r squared plus z squared to the 3/2. What are our integration limits? 0 to r. Okay, and now we've done all the physics, and math happens. And what we get is the charge per square meter, and there's also a 2 epsilon 0. And then it turns out to be a 1 minus z over r squared plus c squared to the 1/2. Now that's sort of a messy formula. So let's consider some special cases. What if we're really close to the disk? Well, let's say z is less than r. So if z is less than r, we get, so this z is negligible compared to, so we're just going to, so we get the square root of r squared, which is just an r, right? So it's going to be a 1 over 4 pi epsilon 0, no, sorry, q over a, we often write it like this, over 2 epsilon 0 times 1 minus a z over r. Yeah.
Do you mind to completely make z over r if z is
Oh.
really small?
Okay, so let's say if z is really, 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 really small compared to r. So we're standing up against this disk, which now looks like a wall, and we can't see the top, and we can't see the bottom, and we can't to the disk. Then it's approximately q over a over 2 epsilon 0, which is nearly constant. Now this is the first way we've found to make a field that's actually constant in magnitude. And we have to be a location close to a big charged disk. But it really is not significantly varying with distance until we get much further away. So, let's see. So basically, here's what we did. We added up rings of increasing radius along the axis, and we got, not surprisingly, a field pointing on the axis. So that was what we did with calculus. Now again, that's on the axis. Nonetheless, if we're reasonably close to the center, maybe it's pretty good. So let's see what happens there. So here's a uniformly charged disk approximated as point charges. And what we're doing is we're calculating the electric field along just one line going through the middle of the disk at the same distance. And we can see that as long as we're kind of near the center, again, it's not diverging very much. So we're So we're close to done with different geometries, but there's one geometry that turns out to be particularly interesting and useful technologically. And it just consists of two of these uniformly charged disks with equal and opposite charges that are fairly close to each other compared to the radius of the disk. This is called a capacitor. And you will use capacitors in your experiments in lab, in circuits. And it's basically just two uniformly charged disks. So one's a plus Q, and one is a minus Q. So, and these are, so they keep going, they're big. So this distance, this gap distance is often called S, and where R is greater than the gap distance, S here. Now let's think about what the electric field due to these disks is going to be. So they're really close. Think two really gigantic disks that are really close together, and we've kind of zoomed in on the middle here. So they go up to the second floor and down to the basement and out in. So what is the electric field going to look like here, or here, or here? Take a second and draw what you think it's going to look like. Okay, so what should I draw at this location? What's the direction of the electric field? Okay, why does it go this way? So this plate contributes a field that way, and that plate also contributes a field that way, and so we have the net field going that way. What about here? Okay, so I'm seeing this way. How does that work out? We have a big arrow for the negative than the positive, so here's E minus, E plus, so we've got, that should be that. So basically we have kind of a small field that way, and over here, yeah, same direction, isn't it? Same. In this case, E plus is bigger than E minus. Now we can do this algebraically. So at the center, oh, we need some geometry here, don't we? So let's put an origin here. Z equals 0 here. So if this distance is Z, then we have we have a Q over A over 2 epsilon 0. 1 minus Z over R, right? Plus another Q over A. And then here we've got, what's that distance? That's S minus C. So we have Q over A over 2 epsilon 0, 1 minus S minus C over R, if I did that right. And outside, we can actually derive expressions for the field outside, and it comes out to be well, actually, if we just simplify this, it comes out to Q over A over 2 epsilon 0. We just do the algebra here. Times a 1 minus S over 2 very close to Q over A over epsilon 0, actually, inside. We can actually do that mathematically and numerically and see how it so this is just a little program that graphs the field of the contribution of the positive plate, so that's a 1 minus C over R. The contribution of the negative plate, 1 minus S minus C over R, adds them together, and then it plots the contribution of the positive plate, the contribution of the negative plate, and the net field here. And we're just going to do it as Z goes from S, which is the separation, to S over 50 here. So what we get is the red is the contribution of the positive plate. It's falling off very slightly. So as we're moving across here, okay, from the center in. We find that those two things, even though they're both varying slightly, when they add up to something, the thing they add up to is super constant. So in fact, inside this capacitor, which is big plates in the electric field really is just plain uniform. And so that's a way to make a uniform electric field. Okay, let's apply this. So suppose we have a capacitor whose radius is 50 centimeters. And the gap distance is 1 millimeter. And let's say it's filled with air. So there's air between the plates. Now it turns out when the electric field in air gets to about 3 times 10 to the 6th newtons per coulomb, air becomes a conductor instead of an insulator, and you get a spark, and you get charge flowing, which reduces the charge on the plates and therefore the field. So the question is, what's the maximum charge we could put on one plate of this, on this capacitor, before we got a spark and the air ionized? So how would we figure that out? Think about it for just a second. What? That's what I'm asking you. What's the maximum charge before you get a spark? So remember that A, this is pretty good, and B, approximations are your friend. We wouldn't bother deriving all these approximate equations if we didn't intend to use them. So how do we figure this out? Altera? Do what? Is set Q over A over epsilon 0 is 3 times 10 to the 6 newtons per coulomb. And so Q is going to be 3 times 10 to the 6th newtons per coulomb times epsilon 0 times the area of one plate, which is what? Pi times times 0.5 meters right? So what does that come out to anyway? Let's figure it out.
You only want to square the 0.5 meters, not the pi.
Right. Don't want to square the pi. Okay, so epsilon 0 equals 9 points. What is it? It's well, it's 1 over 4 pi epsilon 0, 1 over that times, so 8.85 times 10 to the minus 12th. And this would be Coulomb squared per Newton meter squared, right? And area is pi times 0.5 squared, and E is 3 times 10 to the 6th. So Q is equal to E times epsilon 0 times the area. Print Q. Is that right? Looks right. So about 2 times 10 to the minus 5th coulombs. So I want to come back to rings for a minute, because we can do something else with rings and answer a question that has puzzled many of you very reasonably, which is why we claim that the electric field of a uniformly charged hollow sphere is 0 everywhere inside and looks like a point charge outside. So here is, it's a little hard to see, here's a sphere. And what we're going to do is, since it's a hollow sphere, we can actually just cover it with rings. But they're not, on the disk we just had rings that got bigger and bigger. Here they're going to get bigger and bigger, but their z position is also going to change, right? And we can just add up the field of all these rings to see what we get. So basically the theory is, so here's a ring, and there are two arrows here. One is the orange arrow is the net field at that location, and the green arrow, which is offset, is the contribution of this ring. And it really should be in the same location, but then we couldn't see it, so we've just moved it off here. So we are going to approximate the sphere with a bunch of rings, and the contributions are getting smaller and smaller, but the total's getting bigger and bigger. Whoops. Sorry. Okay, so, and eventually we just get, so this is a very small contribution, and that's our net field. Now we just did it numerically, but it can be done with calculus, and this is in chapter 15. It's a section that's not assigned reading, but it's at the end of the chapter, and if you just like to see how it works out with calculus, you can look at it. The more interesting situation is inside the sphere. How does that actually end up being 0? So we're going to do the same thing, except put our observation location inside the sphere. Okay, and notice that, let's make that a teeny bit smaller. Notice that so here's the sphere. It had to be kind of pale so we could see inside it. Again, here's our observation location. Here's the net field, and here, just offset a little, is the contribution of this ring. And notice that we're not doing it at the center. Okay, we picked a place that's not at the center of the sphere to do this. So as these rings get bigger and bigger, they make big contributions. But as they get bigger, all the charge is getting a little bit farther away from our observation location also. So the individual contribution is already decreasing here. And so we see that, okay, so we're nearly just at the center of one ring, and so its contribution should be 0. And now what's going to happen as we get rings on the other side of that observation location? Yeah, they're going to start contributing a field in the other direction. So you can see this little contribution to this ring is actually now in the other direction. And as that contribution in the other direction gets bigger, the net field starts decreasing as we add it up. And now there's a lot of charge on these rings, but they're kind of far away, so they're making small contributions, and we get to the end, and you can just see the little tiny contribution of the last thing, and the net field here, which is that little tiny orange square. Now it's not exactly 0 because the rings are actually pretty widely spaced on this calculation, just so we could see inside the sphere. But it's remarkably close to 0, even with rings that are that widely spaced. And so if we have the spacing of the rings, it would be even closer to 0. And if you use calculus, it turns out you can actually prove that it really comes out to 0, no matter where your observation location is anywhere inside that ring. So the mysterious assertion that if you have a hollow sphere uniformly covered with charge, makes an electric field at any location inside that sphere that adds up to 0, we can actually prove and see how it works by adding up the electric field of rings. And because of the symmetry of a sphere, you know, if we'd wanted it up here instead of down here, all we have to do is rotate our axes. It comes out the same, right? So this is true for anything inside the there's also a section to read in the book, which I'm not going to go over now. It talks about a sphere that's not hollow, but it's solid and it's charged throughout its volume. So how can you make a sphere that has charge all the way through its volume inside? Well, you could have a nucleus. That would be one thing, an atomic. Or you could shoot ions into some material with one of the accelerators downstairs and embed them inside this material. So, and that's a kind of interesting. So basically, what you're doing is you're going to, in this case, you're going to get the electric field at some location inside, you're going to add up little spherical shells of charge, so little spheres of charge which look like point charges. And so the key is figuring out how much charge is in one of these spheres, and you have to consider the volume charge. But and it turns out to go like R. So E increases with R until you get to the edge, and then it starts the 1 over R squared thing. So, so questions about this general procedure? Yes? Oh, if you go far enough from a capacitor, does it look like a dipole? It definitely has some dipole character, doesn't it? Because it's got this equal and opposite positive, negative charges. And so if you looked, so if you had, so you have these two charged plates here. Yeah. So we've got field here, field this way, up here the field's that way. That's the location, direction of field in the rod, in the capacitor. And presumably it actually does have some sort of dipole pattern outside it, yeah. Now capacitors are often made, the ones that we use in circuits are often made of two sort of thin strips of something like aluminum foil with a piece of wax paper in between them, so it's not a conductor, and they're rolled up, so they're not necessarily spherical. But the principle, yes, you would it certainly has a dipole-y kind of character, doesn't it? I want to talk for a minute about what's going to happen in lab this week, because it's sort of interesting, I think. So what we're going to do is watch a video, which maybe I can show you here if it behaves, that is supposedly a video of a demo done on the International Space Station. Involving a charged knitting needle and charged droplets of water. And no, I don't want notifications. Thank you. And the idea is that this person rubs the knitting needle with paper in this case. And it turns out that if you squirt a liquid out of a spray, any kind of atomizer or a spray can or something, those droplets are often charged just because of the friction of coming out of the nozzle. So charge is plausible, but what he actually seems to get, and we'll see if the audio wants to work or not.
Okay, I've got it on pause, and what you're looking at is a knitting needle. And I happen to have in my crew preference a couple of knitting needles. And not that we have a lot of time to do knitting up here, but there's some other neat things you can do with them. And so watch this. So here I have a piece of paper, and I come up with the knit needle with a piece of paper. And this knit needle is a polyethylene knit needle. It's 8 millimeters in diameter. And now I'm going to take a syringe with a little Teflon cannula. I'm going to squirt drops of water out, and look what happens when those drops of water get close to that charged knit needle. So this is like a little satellite going around a cylindrical shaped planet. Except the physics here is a little bit different. It's not about gravitation. It's about charge forces. And of course, charges can exert a potential field, as we call it. So it can exert.
Okay, we might not call it that in our physics class, but.
So you have a charged drop that was ejected from a Teflon tipped syringe. And then you have the charged knit needle. And they're going to be attracted if they're opposite charges. But because the drop has some velocity to it, it's orbiting around the knitting needle. Now this knitting needle happens to be a little different. I mean, when we started out, this knitting needle is made out of Teflon. And Teflon has some really neat static charging properties when you're rubbing. And I figured it'd be good to have a Teflon knitting needle when you're on station. Now look at this droplet. It's orbiting around, and since we have cylindrical geometry here, it can recess down the cylinder, but then it gets to the end, and it reverses its direction and winds back along the cylinder. So it seems to be trapped. And here we have some little tiny droplets. They kind of remind me of a picnic out in Houston. And these droplets, the bigger ones that you see there, are about 6 to 7 millimeters. That Teflon rod is about 6.5 millimeters in diameter. And here you see a bunch of little tiny droplets, and they're making spirals. And they go down the cylinder for a while, and then they'll reverse their direction and spiral back. Now, if you look closely up in the upper right-hand corner, you'll see the injection nozzle from the syringe, but you also see that I have a second knit needle, actually a third knit needle.
Okay, he's getting complicated. But, okay, so the question is this real? Okay, so then you ought to be able to make a model that would do the same thing. So what you're going to do in lab is build a computational model, the charged knitting needle, which looks a whole lot like a uniformly charged rod. But why would they reverse direction? Why? Okay, so there's some questions here. So what we're going to do is try to model this and see if we can actually get the behavior shown in the video. And that's lab this week.